All right, we're going to go ahead with continuing on with Chapter 1. We're going to do Section 5. So let's get started. Okay, in this section, we're going to cover measurement uncertainty, accuracy, and precision. We're going to define accuracy and precision. We're going to distinguish exact and uncertain numbers, correctly represent uncertainty in quantities using sig figs, and apply proper rounding rules to computed quantities. Now, these last two, we're talking about sig figs and rounding numbers. We're going to do quite a bit of that in class, so I'm going to briefly cover it and give you the rules so you can get it in your notes, and we will go ahead and practice that in class with a bunch of numbers and exercises and stuff to make sure you get it down. It's critically important for the ACT test because you will have answer choices to questions where you'll need to know the exact answer. They'll give you variations, for instance, of the same number, which would be the correct number, and you'll have to pick out which one is correct according to the sig fig and rounding rules and stuff like that. So we want to make sure that you get these down pat and get them right, so that way you can pick up a couple points on the ACT test just because of this. So we'll spend some time working on that in class. All right, so let's go ahead and take a look at counting numbers and defining quantities. If you look here at the carton of eggs, you can see there's 12 eggs there, a dozen eggs, and you can of course easily count those: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Now, we would consider counting numbers to be exactly correct, exact numbers, right? There's 12 eggs, there's exactly 12 eggs. There's not 12.1 eggs or 12.5 eggs, there's 12 eggs. Simple. Now, if you look to the lower right, you've got a ruler. A ruler is 1 foot, or it has 12 inches, whichever you'd like to say. It's a conversion factor if you want to look at it like that. But in either case, that's also an exact value, right? We know a foot is exactly 12 inches. So those are both examples of counting numbers and defined quantities being certain values that we know exactly. So what we're going to talk about here a little bit is, what about if you don't know something exactly, like you've got to estimate, as in the case here with the graduated cylinder. So if you look here at the graduated cylinder, right, you got this meniscus, okay, if you remember that from physical science, meniscus, and that's that curvature you get, sloppy curvature, but it looks like a smiley face kind of, and it's an effect. It's a mixed effect between gravity pulling down and capillary action pulling the water up the sides of the graduated cylinder. So maybe you remember that from physical science, maybe you don't. We'll talk about it later in the year, because we'll be covering this more in depth. And if we enlarge that, you can see here, right? So you got increments of 5, 10, 15, 20. And now you got increments of ones. When you look here, 21, 22. So 21 right here, 22 right here. So we can see this curvature is somewhere between 21 and 22, right? So we got 21, 22, and when you measure a meniscus, you measure it from the center, from its lowest point. Okay, so this probably somewhere in here is the lowest point. Enlarge it even further. You can see right here, you got to make a judgment call, right? You know it's 21 because it's greater than 20. It's greater than 21, but it's less than 22. So you know 21 is significant, right? What you don't know for certain is what this last value is. Is it 21.4, 21.5, 21.6? Who knows, right? Some of you may say 21.4, some may say 21.5, 21.6. The bottom line is we're certain about the 2 and the 1, right? The tens and the single digits, but we're uncertain about this last value. Okay, we don't know that, and that's where it comes into play with significant figures. Now again, just to review real quick, when you measure a meniscus, look at it at eye level. You want to crouch down if you have it set up on the desktop in the lab. You want to kind of bend over a little bit, crouch down, what have you, and read it at eye level. Because if you look at it from above or from below, you're going to get this effect of parallax, and that's going to give you a different value. It's going to give you a different reading. And instead of being this close, 21.45 or 6, you may end up at like 22.5 or 20.9 or something like that, depending on which angle you're looking at it. So please read these at eye level. All right, so let's go forward and let's talk a little bit about some of these significant figures. If you read in OpenStax already in the chapter, you probably saw that it talked about captive values and leading values and trailing values. And that's all well and good. And the captive are pretty simple, right? They're the zeros that are between two significant numbers, and the significant numbers being something like a 1 through a 9. And the leading zeros are the zeros that are out in front. We oftentimes call those placeholder zeros. What happens where we have to make a decision on what we're going to do is with that last zero, those zeros to the right, the trailing zeros. And so I'm going to give you some rules that'll help out with all cases, I think, when you get to these values about determining what to do and picking the right answer option. And so we'll practice these all year, and by the time you take the ACT in March or February or whenever it is this year, you should be in really good shape. So let me give you these rules. And these are not in your book, so go ahead and write these down in your notebook. I'm going to give them to you from another textbook. And the first one is non-zero numbers are always significant. Non-zero numbers are always significant. What's a non-zero number? Well, a 1, 2, 3, 4, 5, 6, 7, 8, 9, or 10. Okay? So anything that's not a zero, those are always going to be significant. In other words, they're always going to matter. They're always going to be counted. Now, the second rule is zeros between non-zero numbers are always significant. And this is like your captive zeros. I did it again. Alright, that's not too bad. We'll ignore that. Alright, so if you have let's say you have a number like 605, right? That zero is between two non-zeros, so that makes that zero significant because it's, as the book showed you, it's captive. It's held between two significant values. So that makes it significant. Oops, sorry about that. 3. All final zeros to the right of the decimal place are significant. All final zeros to the right of the decimal place are significant. Okay, let me give an example of what that would look like. So let's say you have something like 6.20. Okay, you've got a significant value here, and you've got a zero now that's to the right of the decimal. And because it's there and it's to the right of the decimal, we took the time. We didn't just write 6.2, rewrote 6.20. We are now indicating that we are that accurate. We are accurate to the point that we know it's not 6.2, but 6.20. We know that 2 is significant and that we're pretty darn close with that 0. Of course, the last value is always a little bit questionable, but we know it's probably like 6.19 or 6.21. So we're saying this one's a little bit uncertain, but it's significant. And or we're either accurate to that value, 6.20 exactly. In either case, if it's a 0 to the right of the decimal, we're going to call it significant. It's gonna be an important value. And here's the trick. Here's the last one. Zeros that are placeholder zeros. These are your leading zeros or trailing zeros. So zeros that are placeholder zeros are not significant. And I'm going to add a little piece of advice here. Put the value in scientific notation. I'll put an exclamation mark behind it and I'll underline that. Okay, so let me show you why. Okay, let's say you have something like 0.0253, right? Now to put that in scientific notation, and I don't know if you remember scientific notation thoroughly or not, we'll review it here shortly, but the bottom line is, remember, you got to move your decimal to some position that it creates a value that's going to be 1 or greater, but it's going to be less than 10. Okay? In other words, if I move my decimal here, it's 0.2, right? So that's less than 1. It's got to be 1 or greater. It's got to be equal to 1 or greater. And so if I can't stop there, I got to keep going. So I go one more spot. Now I'm at 0.2, or excuse me, I'm at 2.53. Is that something that's greater than or equal to 1? Yes. Is it something that's less than 10? Yes. So I can stop there now. I can't keep going because if I go to 25, then it's gonna certainly be greater than or equal to 1, but it's gonna be greater than 25, not less than, or excuse me, greater than 10, not less than 10. So 25 is too much. I would have to go back and move my decimal again back one spot to here. So this would be the right thing. And so when you rewrite this, you get 2.53. And you moved your decimal 2 spots, so it's going to be times 10. And remember, when you move your decimal to the right, it's negative. When you move your decimal to the left, your exponent value is going to be positive. So I know this is going to be negative, and then you tell it how many spots you moved. I moved it 2 spots. So there you go, 2.53 times 10 to the negative 2. Now the important thing here, and where significant figures come into play, is when I put it in scientific notation, look at what happened to those placeholder zeros. Where did they go? They disappeared, right? So they're not important. They're not significant. So if you can get rid of the zeros when you put it in scientific notation, then that's a good indication that those values are not significant, that they're just placeholders, and that you can drop them. You can get rid of them. Okay? All right, that's good. Let's go ahead and move on and talk about rounding values. I think that's our next point here. So let's go ahead and take a look at that. Rounding rules. Let's talk a little bit about the theory here with rounding rules, because you've always been taught you've got 1, 2, 3, 4. Which way do you round? You round it down, right? But then you get 5, 6, 7, 8, and 9. And which way do you round when you got those values? You round up. Okay, now this is where the math people hate us, science people, because we say, well, that might be acceptable in math. It's really not. That's not acceptable in science. And let's take a look why, right? How many values you got here? You got 1, 2, 3, 4. So I got 4 values there. How many values you got here? 1, 2, 3, 4, 5. I've got 5. That means, in other words, 4/9 of the time you're rounding down, and 5/9 of the time you're rounding up. Is that equal? No, it's not equal. It's not equal at all. So what we do in science, because a lot of times you're going to be, you'll have a value and then you'll round it and you'll add it or multiply it or divide it by some other value, and you'll do something else with that to some other value, so on and so forth. And by not having these values balanced, okay, then you're going to go ahead and cause inaccuracies, okay? And you're going to compound your error by multiplying, dividing, adding, and subtracting inappropriately rounded values. So here's what we do. And it's quite simply this. If you have 1, 2, 3, 4, you go down. 6, 7, 8, 9, you go up. The question is, what do you do with the 5? So what they've decided to do is split it, so that way we get a 50-50 shot, right? Because 1, 2, 3, 4, that's 4 times, and this is 4 times. Now, what if we could do something with this 5 that it's a 50-50 split on whether we go up or down? Well, then we would be like 4, and then with the 5, we'd be like 4.5, 4.5 times we go up, 4.5 times we go down, and that's going to be an even split rather than 4/9 and 5/9. So we take this 5, and here's the rounding rule. If your value ends in 5, you look to the number before it. So let's say I have 1, 2, 3, 4, 5, okay? 1.2345. So if your value ends in 5, you look at the number before it, okay? If the number is even, you are going to stay the same. Stay the same. In other words, you're just going to drop the 5. Okay, so this becomes, like I said, you end in a 5, you look at the number before it, it's a 4, it's even. So we're going to stay the same. We're going to keep that. We're just going to drop the 5, and that's going to become 1.234. Now, what if you have 1.235, where you end in a 5, you look at the number before, and it's now odd. In this case, you're going to round up. And so that's going to become 1.236. Okay? So notice what you did here. You can call it rounding down or staying the same or whatever you want, but you dropped the 5 and you kept that, right? So you went down when it's even. When it's odd, you went up. So it's a 50-50 split. And so that's what happens when we get to 5. Okay? And those are the rounding rules for chemistry and for science. All right. Another thing we're going to need to consider is what to do with accuracy and values, right? What if you have two different numbers? In this case here, how many significant values do I have? I've got 1, 2, 3, 4, 5, right? There's no zeros there, so each one's significant. The 6, the 9, the 6, the 5, and the 8. So I've got 5 sig figs there. 5 significant figures there. And then right here, how many do I have? I've got 3. And here I've got 3. And so the rules basically tell us that we cannot, when we add, subtract, multiply, divide, we can't have a value that's going to be more accurate than our least accurate value. So here, how many degrees of accuracy do we have here? Well, we're going to tenths, hundreds, thousands, right? Tenths, hundreds, thousands, at eighths in the thousands. So we got 0.658 thousandths. So that's pretty darn accurate, right? We're going 3 decimal spots, or 3 positions to the right of the decimal. That's pretty darn accurate. Whereas here we're only going to the tenths, 1 spot to the right of the decimal, right? So you can't be more accurate than your least accurate value. And in this case, both of these numbers here are 3. Our least accurate value has 3 significant figures. So our answer, we know, whatever that comes out to be when we're done, our answer can only have 3 significant figures. So let's take a look at what that looks like. Okay, so let's say we're going to do this problem. This is a density problem, right? We want to figure out the density of the rebar. Okay, we don't know what this rebar is. We know what the mass is. So remember, density is mass over volume. So we know what the mass of the rebar is. It's 69.658 grams. And we know what the volume is, right? You look here again, you got to estimate, right? Here we got 5, 10, 11, 12, 13. It's not quite to 14. It looks like it's somewhere in between. Let's call it 13.5, right? And they did that for us already. They showed us that was our initial volume. You put the piece of rebar in the graduated cylinder, the water goes up. And when it goes up, they're saying this value here, right? It's 5, 10, 15, 20, 1, 2. 22, it's not quite to 23. They're actually going to say they read it and they're going to tell you it's 22.4. Okay, so to get the final volume, we've got 22.4. Now, so how much water did this rebar displace when you put it in? Well, 22.4 minus 13.5, the final value minus the initial, gives you let's see, 14 of minus 5 is 9, and you have 8. So you have 8.9 milliliters, right? And I think that should be right. 21, 22.4. Yeah. Okay. So now let's go ahead and do our math. So I have 69.658 divided by 8.9. And my answer comes out to this really long number, right? It's going to come out to 7.826741573. That's what shows up on my calculator screen, right? But we said how many numbers can we have in our answer? We can only have 3, right? So we got to start with the left, right? We got to count from the left to the right. So we got 1 digit, 2 digits, 3 digits, right? Now this 6 tells me, right, I'm going to round up, right? My rounding rule is going to round up. So that's going to end up to be 7.83, and that's grams per milliliter. and that would be your accurate answer, right? Now beware, because this is where the ACT is going to give you, answer choice A is going to be like 7.826. Answer B is going to be like 7.83. Answer C is going to be like 7.8. Did it again. 7.8. And then answer D would be something, I don't know, 7.8 times 10 to the 0 power or something like that, right? So they're all relatively correct answers to some point. All right,